Hello, everyone. My name's Charles Godfray. I'm the director of the Martin School where you are, and welcome to the Martin School. Just before I introduce today's speaker, I'd like to introduce my co-host who will be taking the questions, and that's Sir Andrew Pollard, Andy Pollard. Andy's Professor of Paediatric Infection and Immunity here, Director of the Oxford Vaccine Group, and you will, I think, probably all know him from his work on the Oxford AstraZeneca vaccine. And more parochially, he was a program leader of one of our programs at the Martin School on the collective responsibility for infectious disease. But it gives me an enormous pleasure to welcome Sir Patrick Vallance to the Martin School. It is a cliche to say someone needs no introduction, and you're probably one of the few people where that is true, but I'm going to very briefly say a few words about you. Patrick had a distinguished career in clinical research on vascular biology and related topics, was head of medicine at UCL, and then in 2006 moved to GlaxoSmithKline, initially as head of drug discovery, and then latterly as head of research. In 2018, he moved back to the UK to become government chief scientist, which is an influential role that is largely behind the scenes, but of course not in the last few years with the pandemic, when Patrick became just this huge public figure. Patrick stepped down in 2023, and I'm delighted to say his successor, Dame Angela McLean, is in the audience with us this evening. And Patrick is now chairman of the Natural History Museum, and he has so many honours that I have permission not to go through them, otherwise it would take up all the talk. So Patrick, welcome, and tell us about why governments need scientists.
Thanks, Tim. Well, thank you very much indeed. Great pleasure to be here. I think this is the second time I've spoken at the Oxford Martin School, so it's lovely to be back. And I feel slightly embarrassed, actually, with this title in a place which is dedicated to try and bring research together for practical impact, because it's sort of so obvious why government may need scientists. But I'm going to nonetheless go through some of my thinking as to why this is an important area for government. And I want to start here, which is I can't think of a single area of government policy or operational activity where science, engineering, and innovation couldn't make a difference. So whether that's how we think about our food supply, the way in which we produce food, our food security, whether it's how we think about our housing, the types of housing we want, the types of cities we want, the way in which cities and towns work, our power supply, of course, our energy supply, the goal of net zero. Health is absolutely dependent upon technological advances, science from behavioural science through to medical science. Our transport system and how we get around the country and indeed get around to other countries is critically dependent on understanding these aspects of science, technology, engineering. And of course, the way we communicate with each other or the way in which we educate our children. So every single department that you think of in Whitehall, or indeed in any government, has a science, technology, engineering need. If that wasn't enough, that it is in fact ubiquitous across all policy decisions, then think about the economy. And 7 out of the 10 biggest companies in the world are based on science and technology, and they grow at a faster rate than other companies. And countries which are good at science, technology, and the application of that in a business sense do better than those that don't, have greater growth and greater productivity. And then on top of that, if you think about national security, whether it's conventional defense, where you now see that, of course, technologies and the ability to master those technologies is crucially important for security, or whether it's natural disasters, you can see that resilience is dependent upon science, technology, and engineering. In my time as Government Chief Scientific Advisor, the issue of resilience, of course, became a very big one for science, technology, and engineering. And in fact, a few weeks into the job, the first thing I had to deal with was the Novichok poisoning. The next thing that I had to deal with was, you may remember this, drones over Gatwick one Christmas, when I found out there weren't many people who knew about how to stop drones over an airport which wasn't a military airport. The next one was actually shown here, which is the Toddbrook Reservoir Dam that got very close to collapsing one summer and needed advice mainly on the engineering side, and then of course COVID, which I will talk a little bit about. But my point is, if you accept that every single department has a science, engineering, technology need for policy, every single part of policy, and the economy is highly dependent on how well you do at this, and national security and resilience is highly dependent on doing this, you'd really hope that governments were good at it. And this has been noted in governments right away around the world. And of course, some are taking this very, very seriously. How do we make sure that we are good at this and we are enabled to be informed by science, technology, and engineering when we make decisions? So the first question is the government good at it? And I want to go back just a few years. This was some work that we did that was published in 2019, asking the question about the state of the science system in the UK government. And we found a number of things. We found that science budgets had been actually disproportionately reduced in most departments. Not all, there were some protected departments, health and defence were two protected departments, but in other departments there was a very clear reduction in science budgets over at least a decade. There was lack of a clear model of science leadership in many departments. In many cases, it was a single science advisor with no team around that person. And it's very difficult to influence policy decisions or to inform policy decisions if you're a lone operator, particularly if you're a lone operator that isn't part of the executive team of that department. So we thought there was a sort of structure about the leadership of science. We thought resources, so the sorts of infrastructure that would be normal to a scientist in academia or in other places, wasn't necessarily available. And we were worried that some of the public sector research establishments, so the bodies that are undertaking research, for example, the Met Office, which is a very good one, and several others which had been not so well looked after as the Met Office. These were the ones we were concerned about. You know, what happened to those as they got devolved from government? Did they have the right infrastructure? So we were worried about some of the sort of structural points. But this, I think, is the most striking thing to think about. Of the fast stream, so this is the graduate intake for the civil service, so you can pretty much guarantee that the shape of the civil service will reflect in 20 years' time the graduate intake today. And the graduate intake at that time, there were 1,200 people on the graduate scheme, of which 24 were on the science and engineering fast stream. And of the 400 on the generalist scheme, so this is the scheme that largely focuses on policy people and the general running of departments, of the 400 on the generalist scheme, 45 had a STEM degree. So we're talking about 11% or so of people on that course had a STEM degree, the vast majority arts and humanities graduates. Now, arts and humanities graduates are incredibly important in government, but it can't possibly be right for it to be a 90-10 relationship. So what we really found was that the government hadn't kept up with where it should have done on the support to science and engineering across all domains, and we were worried about the general structure of the civil service going forward. Now, from this, actually, quite a lot happened. So I think there was a sort of some embarrassed shuffling when this came out. That yes, this was a problem, and we now know that the number here, I can't remember exactly what it is now, but it's sort of 80 or so it's got in the right direction. And the percentage target for the general fast stream is now 50% of all the fast stream should have a STEM degree. That's an arbitrary number. It seems perfectly reasonable as a goal to say 50%. And there have been some increase in budgets, and there is a much clearer model of science leadership. So I'd say the government actually has listened, and things are pointed in the right direction. They're definitely not where they need to be yet, but they're pointed in the right direction. Now, government, of course, doesn't just depend on the science inside government. It depends on all of the science in the country. And this is also from around the same time. So I'm deliberately using data from around the same time. If you look at the foundational science base, so by which I mean the academic and research institute science base, I think by any measure, the UK is world class. And at that time, we have less than 1% of the world's population, but 4% of researchers, 7% of academic publications, and 14% of the most highly cited papers. So that's pretty good. And we have 3 out of the top 10 universities. That number moves around a bit, but we're in good shape. And there was a potential for increase in research funding. So it looked pretty good, and it is pretty good, but there's a sort of warning signal here, and I think Paul Nurse's recent report highlights that there are no guarantees we keep this position. This needs active support from government, and we can't assume that we will remain in the same position. And we know that many other countries are investing very heavily in their academic base and their research base. So whereas, for the government bit, I said, pointed in the right direction and lots to do. On the sort of foundational research base, I think we have to say we're really good at it, but don't take that for granted and don't rest on your laurels. And I'll come back to this point. Government, academia, and the third bit that we need to think about is industry. And here, it's an interesting story. So we have a large industry base, which is partly dependent on science and technology. So we've got very, very good major pharmaceutical companies. We're overrepresented by those, and that is a very R&D intensive sector. We have good engineering in part, Rolls-Royce and other companies, and we have good defense engineering companies, and we have some others as well, including in parts, for example, on semiconductors and so on. So there are bits where you can see that we're good, and there are some large companies which have an important sort of foundational base in the UK. If you look at the startup situation, we're much, much better than we were, and we're much better than most or all of Europe, actually, in terms of startups. And here is the sort of normalized rate of growth of venture capital deals into deep tech companies. So companies that are inventing or using tech to do things rather than companies that are just using technology as part of their other activities. So these are companies actually making tech. And if you take 100 as a baseline, obviously the baselines were quite different because the US is much higher, but you can see the rate of growth is roughly the same in the number of companies, UK, US, and rest of Europe. So that's pretty good. But if you then look at the deal size, so the amount of money that goes into that, and again, starting from 2011, finishing here at 2020, you see the US massively outstrips the UK and Europe. And that remains the case, although, again, getting better for the startup phase. So if we look at big companies, we've got some pretty strong companies, probably not enough, and not enough variability in the areas we're in. If you look at the startup phase, we're much, much better than we were. We've got lots of companies. They are not as well capitalized as they probably should be, many of them, and that's a problem. But where we definitely have a problem is in the scale-up phase. So the number of companies that reach, let's say, an arbitrary $400 million valuation, the number of those that can go beyond that to become independent, scaled companies with products and incomes that could be the big companies of the future is where we definitely have a gap. And that gap is a very significant gap in terms of the sustainability of the system, and one that needs attention if we're going to really capitalize on this. So just to pull that together, government, as I say, sort of gets it that it needs to do something, and it's pointed in the right direction. Academia, foundational science-based research institutes, very good, don't rest on our laurels. Industry, good in parts, but a gap in terms of scale-up. What I want to do is to think about those three things as an integrated issue for science and technology. In other words, it's very easy to think of science and technology as something that is only one of those three, but in fact it's all three. And I think the importance of these three things and the importance of the notion that they are foundational to the country means that this is a prime ministerial accountability. So it's great to have a science minister, it's great to have a science department, but when you think of the breadth of the impact we're talking about, this has to be something that a prime minister needs to take an interest in. And so the formation of a prime minister-led National Science and Technology Council is an important step for this country. And it's very important that whoever wins in the election this year takes this very seriously. Because when you start to work across Whitehall, only prime ministerial authority really brings that together. So the notion of having the Prime Minister chairing a National Science and Technology Council, as indeed the Prime Minister chairs the National Security Council, I think is important. Now, one of the reasons that we pushed for this to be set up like this was that the National Security Council has worked for many years with the Prime Minister chairing it. It has that attention that comes from prime ministerial ownership of it. And we think that the Science and Technology Council needs the same thing. And so we thought, well, why not just mimic the National Security Council? And something I said at the time was, it needs to be as inconceivable for a Prime Minister to come in and say, you know what, I don't want that National Science and Technology Council because I don't care about it, as it would be for a Prime Minister to come in and say, I don't care about the National Security Council. Well, rather sooner than I expected, that hypothesis got put to the test when Liz Truss abolished this and actually the National Security Council. But at least it showed they went in parallel. But this is the principle here, that the two things need to be thought of in the same way. And of course, when you think about science and technology in government and what government needs to think about, it is not just how much money goes into the research base. Of course, that's important. But it's everything from what is it we want to do internationally? How can you use government procurement to pull through innovation? What are the financing mechanisms that would allow scale up? What are the talents and skills beyond just who are the researchers, but what do you need to actually use those advances in the system you've got? What's the physical and digital infrastructure you need? And this sort of list of 10 or so things which form the part of this science and technology framework, I think is a useful framework for governments to think of what they need to worry about and what the National Science and Technology Council should be thinking of. So that was the principles behind that, and I think they remain true as a list of things that government really needs to have a plan about. And when this was published, the plans and dates for what should be done were in this document. And I think it's rather important that we hold governments to account for delivering against this, because if we fall behind in this, we fall behind in many other things too. And many of the other things that we know we need to have, like a healthcare system that looks after the population, prevents disease and treats it, are dependent on some of the money you get from doing these types of things. So we have to get this right if we're going to be successful. What I want to do is to give two examples of why this integration between government, foundational science base, and industry is so important. And both examples are ones that are resilience examples, but both of them have huge implications for the economy. And I'll illustrate that first with COVID. So in January 2020, on January the 3rd, I contacted the team in the Government Office for Science and said, I think we need to stand up the SAGE process. And SAGE is the science advice for government emergencies. And it only gets called when there is an emergency, and it can only formally get called when COBRA gets called, which is the ministerial committee that deals with emergencies. But we wanted to get the process started. And early in January, of course, one of the things that was possible, because of the very strong science base in the UK, was it was possible to find experts. It was possible to find experts in epidemiology, in behavioral science, in mathematical modeling, in engineering, in veterinary science, in virology, in immunology. And those people could rapidly be assembled to give advice on this potential new emerging threat. And so the very fact that we have that strong and broad science base was an important part of the response and will be the important part of any future response. And if you think about the academic contributions during COVID, and Oxford, of course, was supremely important in this, we had an amazing ability to do things around vaccines because there was vaccine research going on, very good vaccine research that led to the Oxford AstraZeneca vaccine. It was possible to get sequencing of the virus done at scale because there'd been a long-term investment in genomic sequencing in the UK, and those people could come together and sequence viruses. And at one point in the middle of 2020, the UK was sequencing 50% of all the viral genomes in the world. So that was because that group could come together under the group called COG UK to make that happen. It was possible to do clinical trials, and again, Oxford was absolutely instrumental with the recovery study in setting up a study that gave answers. Most clinical studies set up during COVID gave no sensible answer. They were too small or too poorly designed, and I'm not talking about tens or hundreds, we're talking about thousands of clinical trials across the world who gave no sensible answer because they were poorly designed studies. The study from Oxford, the recovery study, was the first to show what did work in COVID, and just as importantly, showed all the things that didn't work, despite the fact that people were claiming they did. Why was that possible? It was possible because there was a strong academic base in doing clinical trials in the UK. Without that, that wouldn't have been possible. It was also possible to do things like monitor the spread of the virus because of the academic strengths in epidemiology and in other areas. So that ability to call on people, which may seem very obvious, isn't available in many countries. Many countries do not have that breadth of foundational science, could not do that, and started to look at some of the things that were done here and realize that there were deficiencies in what they were capable of doing. But it wasn't academia alone. So if we go to industry, why was industry important? And I'm going to start with the negative. It was very, very difficult to get testing scaled up in this country. And although a test for COVID was identified quite early on, it didn't scale, it wasn't scaled, and it took a long time to get into the right position. And there are lots of reasons for that, but one reason that I think was important is we don't have a significant diagnostics industry in this country. If we'd had a significant diagnostics industry, that scaling would have been possible. It would have been a different story in terms of the speed at which that could happen. Now, I don't think governments have been thinking of things like diagnostics industry as part of your national resilience planning, but it is part of national resilience. We were able to do some of the things around vaccines because we had large pharmaceutical companies here that were able to work with Oxford to get the vaccine produced at scale. If that had not been possible, it may well have not been as fast to get vaccines out. We had a skilled workforce in this country from industry that allowed all sorts of things to be done in both therapeutics and vaccines that otherwise wouldn't have happened. So again, the fact that we've got very large pharmaceutical companies is a resilience point for the country. And where you don't have those resilience industries, then you have a gap. And sometimes it takes a sort of surprising turn. So one of the surprising turns was when we wanted to try and get a survey going of all of the infection rates across the country and work out what was happening with the spread of the virus. Initially, Public Health England said they couldn't do it. They just simply didn't have the resources to do it. And the Office for National Statistics stepped in and said, well, we'll do it. About a week later, they said, well, we can't really do it because we haven't got enough people to go and take the samples. It turns out that a contract research organisation that wasn't doing clinical studies, because the clinical studies were now all focused on COVID, had a significant workforce that was now not engaged. And the person who was the head of that company had made a very foolish error of boasting to me that he could get these people mobilised within a week. so I said, okay, you told me that a week ago, could you please mobilise them to do this study with the ONS? It turned out they couldn't quite do it in a week, but they did get going. And the reason the ONS study was successful was largely the ONS, but very significantly also the fact that they could get this workforce that was there for a company that existed because of the need to do trials in this country. So that base becomes important. There were other areas, of course, where industry was important. Now, what about government? Well, government, of course, was important for all sorts of reasons, good and bad. But in terms of the science, it was important that we had an organisation that deals in public health. And it is significant that that organisation actually had not had the funding uplifts that it needed over years. So that was an important part, that the infrastructure you fund in public health is crucial. It was important that we had a skilled regulator in the Medicines and Healthcare Regulatory Authority, which became the fastest regulator in the world to approve a vaccine, and indeed was very good also on the therapeutics. And it was important, as I said, that we had the government Office for National Statistics to do that study. So the government part of this was also important. And there was one place in which all three of these got very clearly integrated, and that was in the formation of the Vaccines Task Force. So it was very obvious early on that vaccines would be an important potential way out of the pandemic. And yet, at the beginning, there were no vaccines, and vaccines, on average, take something like 10 years to discover and produce. And very often, when you start to try and make a vaccine, you can't do it. So failure is a likely outcome. But it was obviously important to try to do that. And it was obvious that that wasn't just a procurement problem. In other words, it wasn't like an annual flu vaccine cycle where the Department of Health says, okay, I want to buy that vaccine, can you give me some next year? It needed to be discovered, so it needed a research base. It needed to be manufactured, so you need to understand where things were going to be manufactured. And it needed to be, of course, tested in large-scale clinical trials. And the Vaccines Task Force, I think, was a great example of when you get government people, industry people, academics together, you can achieve an enormous amount. And that was a very well-structured organisation with clear leadership and clear mission. And the mission was a very simple one, which was, can you get vaccines for the population by the end of the year? So that integration of these three things was fundamentally important. And I think, of course, there were individual companies that had to then make it, so Oxford AstraZeneca, Pfizer, Moderna, and others that had to actually make it. But that ability to do that from central government, I think, showed a way of working which showed how important it was to have experts integrated into the system from the beginning. So I'm not going to say anything more about COVID, and of course there's lots of pluses and minuses to what happened, but what was absolutely clear is the science base across those three things became really, really important throughout the pandemic. The other area I want to just talk about is building on that, is the pandemic preparedness. If it was true for the response, it's definitely true for preparedness. And all three need to come together, and all sorts of aspects to pandemic preparedness that we need to think about, from detection to prevention. But there's one that I'm going to just highlight, which was something called the 100 Days Mission, which was led at the G7 in the UK. And the idea was, what would it look like if across the world, within 100 days of a pandemic being declared, you could have a vaccine ready to be produced at scale, an initial regimen of therapeutics, and reliable and approved diagnostics? And if that had been possible for the COVID pandemic, millions of lives would have been saved around the world. I mean, it would have been a really, really major accomplishment. So we set out to say, well, what would it look like to do that? And of course, the first thing it looks like is you've got to have academia, you've got to have industry, and you've got to have government, and they've got to work together. And this is now being progressed across multiple G7s, which have happened since, and with a group that's trying to lead this. But central to this is that relationship between those three areas, if this is going to be true. Interestingly, like all of these things, the initial reaction of almost everybody was, no, you can't do this, it's not going to happen. Now lots of people are saying, yes, it can be done, but it's going to take a concerted effort to do it. Let me move to my second example, and that's net zero and climate. And I'm going to start with this graph. And the reason I'm going to start with this graph is because in 2019, around number 10, there was a growing climate skepticism. There were a group of SPADs who were really determined that the Prime Minister needed to understand that the climate change wasn't necessarily as it was presented, and that the actions may not be needed. They were proposing to call across to the UK various physicists from elsewhere who criticised the climate models. That's quite a problem if you're a chief scientific advisor, to think how to deal with that. And what you don't do is you go in and shout about why it's all wrong. And what we decided to do was to try and get the Prime Minister on a Friday afternoon when he had a bit of headspace, and to give him a 2-hour seminar with two climate scientists and me. And the idea was not to try and be campaigning about it, but to try to just make sure he understood what we saw as the factual basis of these things. And to his credit, he took the 2-hour seminar, and of course the advantage of that, with just us in the room, he could ask daft questions, and no one was going to see him asking daft questions. And I think that was important. But this is the slide, and by the way, the other thing that happened was that I said to the two climate scientists who came with me, we're going to show no more than 5 slides. You imagine how that went down. But we did only show 5 slides, and this was one of them. And many of you will know this. This is the carbon dioxide concentration from ice, and it's taken from ice cores, and you can go right the way down a very long way, a kilometre or more in the Antarctic, and to slightly lower depths in Greenland and so on. And when you bring up the ice, you can then measure the carbon dioxide content. It's been trapped there for all that period. So it goes back to 800,000 years. They're now going back actually to well over 1 million. And what you see when you measure the carbon dioxide content in that ice is it sort of bobbles up and down over 800,000 years. We've had some ice ages and Homo sapiens emerged. And then this red line here, this is not an arrow. This is actually where we are today at the top. So where it says today is where we are. So you've suddenly got this vertical increase in carbon dioxide content in the atmosphere. Why? The Industrial Revolution. And this was the curve, and I can say this because he's spoken about it, that persuaded Boris Johnson that actually this was an important thing. And he became rather an advocate for it there, including during COP26. And it put paid to the climate skepticism that was growing at that time, although it still remains a challenge, as you know. So this was clearly an important step. But what about those 3 different parts? Academia drew this to the world's attention. It was academia who drew the notion of climate change to the world's attention. It was academia who showed how you could measure it. It was academia that showed what might be done about it, and is now showing what the potential tipping points are that could lead us to very major problems of ice shelf collapse, ocean circulations changing, and so on. It's also academia that is beginning to push the boundaries of what needs to happen next in terms of sub-kilometre scale forecasting or understanding the impact of clouds on some of the models. And certainly also pushing the notion that this now is no longer just about mitigation, it's also about adaptation, because the climate has changed, it will continue to change, and we need to respond. Some of the inventions that were going to be incredibly important to get us to at least stop the increase in temperature are, of course, going to need to be developed at scale. And they're going to need industry to do so. So whether that's the obvious ones like electric vehicles, or whether it's carbon capture and storage, or whether it's storage of electricity, all of these things are going to need industrial involvement. And the reason I said that these examples are not just resilience examples, but they're also economic examples, is when governments give clear messages about what they intend to do and the investment that's going to come behind it and the procurement that's going to come behind that, industry is prepared to put money in as well, and to build these things fast and at scale. And that's what's required here, is industry involvement from small companies innovating through to large companies actually making things at scale. And what about government? Well, government's clearly important. It needs to deal with the scale of this. I mean, when you think about retrofitting houses, that is a massive, massive, massive problem. When you think about domestic boilers and moving to heat pumps, those are government things that need to be led by government policy. And government's also important at some of the research funding that can only happen from government. So the fact that down the road from here, you've got one of the world's great fusion experiments and activities going on to try and scale and see whether fusion is possible, and they've had some great advances in the last couple of years, is a government thing. So again, this is exactly the same. If, as a country, we're serious about trying to tackle this, and if, as a country, we want to take advantage of the massive export opportunities that exist here, then those three things need to work together. I'll just move to one other area which builds on this, which is the similar and equally important problem of loss of biodiversity. And this is from Partha Dasgupta's report from 3 or so years ago. He says, we're facing a global crisis. We're totally dependent upon the natural world. It supplies us with every oxygen-laden breath we take and every mouthful of food we eat. But we're currently damaging it so profoundly that many of its natural systems are now on the verge of breakdown. And this is another one that's going to require those links. And I just want to briefly tell you about what I saw as the 4 key questions for a science advisor. The first question is the evidence adequate? And if not, what are you going to do about it? The second is, has the evidence actually been understood, including all the uncertainty and the things that might change that evidence base? The third is, has the evidence actually been presented in a way that's relevant to policymakers? So it's all very well, for example, to tell somebody that the mutation rate of a coronavirus is 10 to the minus 24 per whatever. That's not really relevant. It's very relevant to say, by the way, this is mutating at a rate where something is going to need to be done if you want to stop getting a resistance to a vaccine or something. So framing it in terms of policy is important. And the fourth is, can you actually measure or use science to measure the outcome of your policies? You can check whether you're actually on track. Now, if you look at climate, all of those things actually you get some form of green light on it. Yes, I think IPCC has done a brilliant job of explaining the evidence base, and the evidence base is at least adequate to say, yes, there's a big problem. Yes, it's understood, even though sometimes you might not imagine that from some of the things people say, but it is understood. Politicians do understand that this is a problem. They need to act on it. And yes, that's framed in terms of policy, at least helpfully through the IPCC. And yes, you can measure it with looking at carbon. If you now look at biodiversity, it's almost a red on all of those 4 questions. You know, we haven't really got the evidence base adequate yet. We haven't definitely got politicians to understand that. And we certainly haven't framed it in terms of, so what for the policy, and we haven't got a single integrated measure of what it is we're trying to assess here. And so those are really important challenges if we're going to get this right. And now, you know, I've used this as an excuse to segue to my role in the museum, which is the museum, Natural History Museum, has actually come up with something called the Biodiversity Intactness Index, which is a measure of how much of the biodiversity that existed pre-human interference remains. And in the UK, the answer is about 50%. In other places, it's much higher. There are a few that are lower, but not many that are lower. So there is an index, and what's important about that index is it's now gone onto the Bloomberg terminals, which all the financial institutions use. So once you start to get into financial institutions using it, you then start to put pressure on companies. Am I going to be measuring the impact of what my company does when I do a new development on this or not? And that's what's happened with carbon and the climate, and that's what needs to happen with biodiversity. Seeing as I'm on the museum, bear with me for one more slide, which is, I've talked a lot about the foundational science base, and there's a part of the science base which is often invisible to people, and that's what goes on in museums, and indeed the importance of collections in museums. And I just want to show you two things that have surprised me and made me very excited about the sorts of things that do go on in museums. So on the left is a bat, a stored bat sample, and museums like the Natural History Museum have bat samples going back a couple of hundred years. And the curator of bats, there is such a person, showed me this and sort of took the bat out, and he said, oh, by the way, during COVID, we tried to see, a number of museums around the world tried to see whether you could extract RNA from the bats to see whether they had coronavirus. And it turns out you can from stored bats. So you couldn't have done that a decade or so ago probably, but they can actually detect the RNA. And now there's a project going on looking at the evolution or the distribution, rather, of coronaviruses in bats in stored samples in natural history museums around the world. Now, there's no way, under any circumstances, that the people who collected these bats could have had any idea that that's what they'd ever be used for. And this notion that collections have intrinsic uncertain value for the future is a very important one, I think. And I'm very grateful that people did make those collections, and it is possible to do that. And then the other one is this one, which is an ongoing project. And this is a photograph taken at the bottom of the Clarion-Clipperton zone, which is a zone in the Pacific Ocean between 3,000 and 4,000 meters deep. And the reason that the teams from the museum are working there is that people are proposing to do deep-sea mining in this region. And they're deep-sea mining for polymetallic nodules that contain a number of elements which could be important for things like making electric vehicle batteries and so on. But we know nothing about the biodiversity in this region, so we don't know what effect deep-sea mining would have. And it turns out that 80% of the species that are pulled up or looked at by the team, 80% are previously undescribed species. So we know very little about what's down there. And they just come back from an expedition when I met them, and they showed me something that didn't look as pretty as this. It was a sort of white blob in a Tupperware box, about the size of my fist. And sticking out of the white blob were 6 spikes, like that spike there. And I said, what are they? And they said, glass. I said, what do you mean glass? And they said, well, below 3,000 meters of depth, it's energetically inefficient to use calcium carbonate. So these animals use silica. And they actually make glass enzymatically at 2 degrees centigrade. Now, that's sort of interesting, and nobody really knows why they do it. And there's a rather wonderful thing called the Venus flower basket. If you want to see a really pretty picture of these glass structures, that's got a fantastic one. But these glass spikes, maybe they're for catching whatever bit of light there is, maybe they're structural, maybe they're defense. But the idea that you can make glass at 2 degrees centigrade, of course, is quite interesting from a sort of engineering point of view and a biological engineering point of view. And no surprises to those biologists in the room. Guess what the enzymes are called? Glassins. So there's a whole literature on these things, and of course a potential for thinking about them in terms of engineering. So I want to go back now to the main theme, which is this notion of needing to integrate the different forms of science. And one of the latest sort of funding mechanisms is through this organisation, which was set up a couple of years ago, the Advanced Research and Invention Agency, with the idea of trying to fund things that were deliberately a bit between industry and academia, a bit between government need, societal need, and curiosity, and really difficult. But maybe you could make a difference. And this has just got set up, and I think they've done a fantastic job of actually getting the right people involved. And just to give you an idea of the sorts of things they're doing. And so this is a funding agency that actually gives money out to other organizations and people, but is led, each project is led by a really high caliber scientist or engineer who therefore is on top of where the money's going and what's happening. It's a very different model to the normal academic funding model. And here are some of the first wave of people who put out not their projects, but their perceived opportunities, which they're then going to iterate with others, and come down to then, okay, what does the funding mechanism look like in order to start to do things in everything from insect-inspired robotics here to using the sort of optical approaches that have been used in medicine and other places to look at how you might actually measure climate change, concentrations of things in the atmosphere directly rather than inferring them for climate. So that is by way of saying there's a need to have different and more diverse ways of funding if we're going to really harness this integration between these areas. And my very final slide is a comment that I've talked a lot about structures and organizations and government and so on. But fundamentally, underlying all of this is the need for people who know what they're doing and diverse people. So there is a tendency to think in some quarters of diversity as a nice to have or simply a moral or a social good. It is a fundamental scientific need. You don't answer big problems by groups of people who've all got exactly the same background, all got exactly the same thought process, all got exactly the same training. And so this notion of ensuring a diverse workforce, I think, is underpinning for everything I have said. And I will finish there. That's my thank you slide, but I just wanted to show one more, which I couldn't resist, which is the photograph from the person who won the Wildlife Photographer of the Year competition, Laurent Balester. And this extraordinary looking thing is a limulus crab with the fish swimming above it, and it's been around pretty much unchanged for 400 million years, and is now in some danger, actually. And the reason that matters is not only because of it's in danger, but its eggs that it lays on the shoreline are incredibly important for migratory birds, and they start altering the migratory patterns if it goes. And one of the reasons that this is so widely known about and used as a species is its blood. It's not really blood, but it's equivalent of blood, is bright blue. I don't mean dark blue. I mean really, I'm trying to see if anyone's got a bright enough blue on. They haven't, but I mean it's really bright, light bright blue. And it is exquisitely sensitive to very, very minor amounts of bacterial infection. And so it's used as a way of detecting whether a vaccine or a therapeutic agent has any contamination of infection in the bottle before it's put into millions of bottles, and their blood is crucial for that, and it has been for a long time. But now there are ways to do it without actually having to use their blood, and it's important that we move to those because these animals need to be protected now. So that's instead of finishing on my finishing slide, I decided I had to show that slide. Thank you very much.
Thank you very much, Patrick. A fantastic and inspiring talk. And thank you for all that you've done, I think, from all of us during your time in government, particularly during the pandemic. I think very much appreciated by all of us. And perhaps I can start by asking you about the, not just the civil service, where you described the shortage of individuals with STEM degrees, but also amongst the politicians, where there is a similar problem. You didn't highlight what the numbers were there. I wonder if you could comment on them.
I don't know them, but because it's quite difficult to find out, but it's unbelievably low. I know that. And there is a complete deficit of politicians who have, well, not complete, but there's a very large deficit of politicians who have a science and engineering background. Now, I'm not arguing that all of them should have, but we need some. And I'll give you an example of something. I was in Singapore in November, and I had a meeting with a number of the Singaporean ministers, many of whom have got technical backgrounds, and they asked me a question which I don't think would ever be asked here. They said, how can we use science and technology to monitor whether the policy choices we've made are having the impact we think they should be? I mean, yeah, it's a pretty simple question, but that's not a question that's asked.
So following on from that, I mean, there's a question then of why scientists are not putting themselves forward to be in those positions.
Well, again, I think, so when we looked at the far stream, it turned out, my prior assumption was that probably scientists weren't applying. There was a bit of that. So there was definitely something that lots of people with a STEM degree thought, well, that's not really for me. That's not my background. But actually the numbers applying was quite high. So then my next assumption was, well, they weren't getting through the appraisal system for some reason because it was all geared in the wrong way. It turns out they did get through the appraisal system. The reason they didn't join was that they got offers from other companies faster, and it was just too slow. So actually, this is quite a simple thing to do, speed up the process, and you'll get some of them in. And there are some really, really good people in government who got that, but just not enough. So I think we need to have we'll see what happens now they're moving towards to get 50% STEM graduates, whether they'll get there and whether it's possible then to make sure there are proper career paths. And I don't think the aim is to have lots of people being full-time scientists in government. You need some people doing that. But you also want the generalists, the people who are running big policy groups, you want enough of them to have a science or engineering degree that they infiltrate and change the culture and change the approach across everybody else. So it's that sort of ability to get enough people in there which matters, I think.
So if that sort of moves forward with amongst the civil service, I can see that happening in the way you've described. But then for the politicians, it's going to be much harder because it seems that scientists are not sort of either being selected or don't see themselves in that role. So perhaps your point about the science being understood becomes even more important, but that must be a problem of education at school.
Well, it is, and definitely one of the roles of a chief scientific advisor, and I can see Gideon and Angela here, you spend a lot of your time trying to make sure somebody's actually understood. It isn't enough to say, I told somebody that 2 years ago by giving them a graph or whatever. You've got to test whether somebody has genuinely understood it, and that is important. But I think, yes, there's a problem in terms of thinking about the science education in the school system. But there's another problem as well, which is until we, the public, demand things around science from our politicians, they are not going to care about it because they care about getting voted in. And I think the last time that any politician really, or any prime minister, really sort of hung his hat on the notion that this was important was probably in the 1960s with Harold Wilson and the white heat of technology. And what he said was, this matters to you because your jobs are going to be better, you're going to be paid more. It matters to your children, they'll have a better prospect. It matters to how we as a country succeed in the world. And he sort of made it something that people thought, that is relevant to me. And very often now, I don't think most people think that this is relevant to them, and they don't think that the politicians can really do anything that's going to help them by using science and technology. So I think there is a broader societal question about how can we make it so evident to people that science and technology is the route to some of these success stories, that they care enough about it to be knocking on the door of their MP or council or whatever and saying, by the way, why aren't you using X, Y, or Z to improve our quality of life or our quality of air or our healthcare system?
Patrick, you've lived in a number of different worlds, from medicine to medical academia, and then over the dark side in industry, and then in government. The really dark side of government. With lots of very different cultural environments. And you were, in your talk, were talking about the importance of bringing those together. But they are very different types of worlds that people exist in. So how can you actually bring them together when those cultural differences are major barriers?
Well, I think there are some major differences. There are also an awful lot of similarities. And some of the work that goes on in the public sector research establishments are exactly the same as what goes on in parts of academia. And some of the work that goes on in industry is quite similar to what goes on in academia. And what we don't have is enough movement between those sectors. And I think there needs to be, and people have been saying this for years, so there's nothing new here, but I think there is an opportunity to get this better. We need to have more movement between those sectors so that people have got an experience of more than one area and not to see a career as being bound in one or the other. And you can see this already. If you go to somewhere like Cambridge, Massachusetts,
people are in and out of industry and academia the whole time. I mean, it's very porous. And that's had a really big knock-on beneficial effect for both. And I think you're beginning to see that. You see some of it here in Oxford, you see it in Cambridge, in the UK, you're beginning to see it in parts of London and so on. But we need much more of that. And it needs not to be seen as a one-way move.
So you mentioned the funding aspects of it. So here in the UK, obviously there is science funding from government and from other funders, and particularly in our field in medicine from the Wellcome Trust. But as you're saying, the UK probably hits above its weight as a result of that funding. And you need to do more of that all to make sure it's sustained. But do you know what it is that is making that successful if you were advising the government on how to invest? Is it just more money, or is it something strategic?
Well, I think it's always going to be more money. I mean, because there's a limitless demand. But I think it is definitely about also the way in which we choose to structure academia, structure promotion, structure evidence of success and so on. I mean, those things are all quite important parts of this. And it's why I think the ARIA experiment is definitely worth doing. I mean, it's £800 million, so it's not a huge sum in the grand scheme of things. And it's just got some people doing something quite different. And I think we need to think about the funding mechanisms and whether they're really always targeted in the right way. And I know that's what UKRI has been thinking hard about. The Wellcome Trust has got some new schemes. And I know, for example, the British Heart Foundation decided a few years ago to give one massive grant out of 30 million to one group. Actually, it was a group in Oxford that won it. And I think these sorts of things are quite important if we're going to think about quality, not just quantity.
So in the pandemic, obviously you were part of a remarkable team of people who were, I think, certainly in my view, were the right people there at the right time. And particularly for you, bringing together the different strands of your career up to that point was absolutely ideal. And then you made the decision to form the Vaccine Task Force and to then bring, with the help of the government, bring Kate Bingham on board to do that. And that seems to me to have been different from, I think, any other country in Europe. And in fact, apart from the US, really most other countries. Were you aware that what was happening here was very different? And where did that come from in your thinking?
Well, what I was worried about was when I was asking questions about vaccines, and it was sort of outside my tramlines as a chief scientific advisor, but because I knew the industry and knew what needed to be done, I asked questions, and the answers I got were sort of along the lines of, don't worry, we give flu vaccines every year. Well, this wasn't a flu vaccine problem. We didn't have a vaccine. It had to be discovered, and it had to be made. It had to be made quickly, at scale. And so I worried that we didn't have the right skill sets, and people were unbelievably busy. I mean, DHSC was run off its feet, and they didn't have time to think about this properly. So I just thought, well, I'm going to set up something different and bring in some people from industry. And Kate was obviously an incredibly important part of that and did a brilliant job leading it. But there were other people as well. I mean, a guy called Ian McCubbin, who I'd worked with at GSK, who understood manufacturing inside out. And that's important because in this sort of situation, you have many companies who say, I'm making a vaccine or I'm discovering a vaccine. And they got no idea how they're going to actually physically make the stuff. And Ian is an extraordinary guy. He's very, very, very knowledgeable. He's very unusual in being incredibly smart and having virtually no ego. And he went round and he'd come back and say, yeah, it's a really good project, but you're never going to be able to make it. So don't waste time on them. Go to the ones who can actually make it as well. And that was important. And that structure, I think, of those manufacturing people, scientists, government people was an important integrated structure.
And there's some other differences with countries. The US gave, for each vaccine developer, $1 billion right at the beginning to develop. And I think the UK was quite slow to actually start putting money on the table, which probably slowed down quite a few programs here. And in the end, in Oxford, we got about 30 million, so rather than the billion. But in the end, there were almost all of the vaccine companies didn't develop a vaccine apart from Pfizer. So can you explain why that happened? Why didn't we have the people we should be relying on is industry?
It's interesting. I mean, most vaccines fail, and you did a brilliant job, and in part, I think it was because there'd been funding over the years to get MERS and
a few decades.
Exactly, there was a baseline, and so just chucking loads of money at a company and saying do it, you can see it's not going to work. You need to be really careful about which ones you go with and how you're going to stage that investment, and you also need to be prepared to lose money. And one of the things I think is a really important lesson for innovation for the government is, at the beginning, the most likely thing by far was that there would be no vaccine. Yet you had to do it. Turns out that it did work out. The vaccine was there by the end of the year. Had that not happened, I'm absolutely sure this would have been slated as the biggest waste of public money ever. And yet the two things go together. You can't end up where you end up without taking the risk. And I think that's very important, to be prepared to lose money if you're going to go for an innovation play from government. And I don't think the systems are geared to allow that to happen. And you asked a question about what other countries did. I think most other countries viewed the vaccine problem as a procurement problem, not an R&D, manufacturing and procurement problem. And you're right, the UK didn't get enough money out of the door quickly enough, but in a sense, looking at whatever the amount was from the UK, I don't know what it was in total, but sort of, you said 30 million to Oxford versus $1 billion to a company. You can do that for research grants and everything else. You'll get the same sort of ratio, as you know.
Absolutely. So we do have some time for some questions from the audience. If anyone would like to ask Patrick a question, do put your hand up. There's a question. Oh, there's lots of questions.
Do you want me to go the lady at the back?
Yeah, start at the back. Whoever's fastest.
Hold it right up to your mouth.
Hi, good afternoon. I'm quite amazed by that process of selecting the right scientist to come along with you to, for example, do a mini seminar to the Prime Minister, or integrated the National Science and Technology Council. So if you can perhaps comment a bit more on that process of selecting the right scientists, and also on that council, how scientists are selected, and does it engage with the British scientific diaspora based overseas to identify the international opportunities? Thank you.
Yeah. So on the first question about how scientists were selected for the climate briefing, it was really to get, I can't remember, it was 2 or 3 people I took along with me who had slightly different expertise in it, and ones who weren't going to show 400 slides. Was quite an important part of that. The National Science and Technology Council is not a council made up of scientists. It is a council made up of ministers to think about the science thing, with some scientists there who come from the funding agency, so Angela's there, the Government Chief Scientific Advisor, and a couple of others. So it's about making ministers focus on the decisions that need to be made at an integrated level, rather than simply department by department. But there are other advisory bodies, and the selection of scientists for those for public advisory bodies is normally through a public process of application and selection.
Okay, next question. There's one there. Yeah, go ahead.
Thank you very much. I wanted to ask you a little bit about what it's like to try and convince an elected parliamentarian to invest in long-term projects that will sort of give you dividends far down the stream of when they'll still be in power. And also maybe a little bit about what it's like to have to change your aims and your strategy if a new government gets elected in. If you spent 5 years working on a project only to get told by the next government, we're not doing that anymore. What's that process like, and how does it affect the job of science advice for non-elected civil servants?
Yeah, it's very difficult. I think there's been a real outbreak of short-termism over the past few years, which is a really big problem. And the things that we're talking about here, whether that's long-term pandemic preparedness, whether it's investment in infrastructure to get companies that can grow, whether it's approaches to climate, need consistent long-term thinking. And so again, one of the principles behind the National Science and Technology Council was to look at long-term issues. So it's not every single thing that goes there, it's the long-term questions. And ideally, you would start to get cross-party agreement on that. And now, we're nowhere near that at the moment, but that is what's needed. for these long-term things because you can't chop and change. You can chop and change the individual decisions within them, but you can see what happens. If you suddenly say, I've no longer got this target, or I've changed the date of a target, industry goes, well, okay, I'm out. I can't deal with this. I'm trying to plan on something and you're changing it. So I think that consistency is really important. And I had a very atypical time in government. I had 4 prime ministers, 6 chancellors, 6 secretaries of state, and 10 science ministers in 5 years. If you do the average, I did this little calculation. That's 20 years of service to get to that number normally, but it happened in 5 years. So it's, we have got a short-term issue, which I think politicians need to agree that there are some things that transcend party politics that need to be kept consistent.
Thank you. Of course, during COVID, although we had some very clear direction on certain aspects of the science, although during COVID we had some very clear direction on certain aspects of the science, there were worked out in the media some public disagreements, in particular between the epidemiologists. And in your role, this is new science. What were you saying to ministers about which way they should be going and whether those voices had value and should be considered?
Yeah, so my second principle of science advice was, has it been understood and all the uncertainties been understood? And it's very important that ministers do understand the uncertainty, that they don't get presented with things as black or white, because many non-scientists view science as absolute. It's an absolute truth. I have been told this by a scientist, therefore it's true. Which is bizarre, because mostly what we do is spend most of our time trying to overturn what somebody else thought last week. And actually we get rather pleased when we do it. And that was something that really became an important thing. Scientists like to look at things, take new evidence and say, oh, actually, it isn't what I thought, it's something else. And we get rather pleased. Politicians view that as a U-turn. So that's a really big problem. And so making sure that those other voices are either heard or understood was important. And there were some times in COVID when very, very dissenting voices got to present to the Prime Minister, and he could then see what he thought about those dissenting voices. And that happened, one famous occasion which has been discussed a lot at the inquiry.
Next question.
So, the threatened pandemic in 2009, which I think was swine flu, came to very little, despite the doomsday predictions and appropriate preparedness by government and the NHS, largely unseen by the public. I wondered to what extent you think that blunted the response by politicians and the NHS in 2020.
Yeah, I think there were some things there. So one of the things that was criticised in that period was the stock. It's almost exactly analogous to the vaccine story I just told. There was quite a lot of criticism of stockpiling of antiviral drugs because they weren't needed in the end. But I mean, it's illogical because they didn't know they weren't going to be needed, and if they had been needed, they probably wouldn't have had enough of them. And so that, I think, is a very important dimension of all of this. And I do think there is something about that episode which created a sort of complacency of, well, it probably won't be as bad as people thought, which I think was a problem. Actually, it was a problem right the way around the world. It wasn't just here. But except in countries which had SARS and MERS, who were actually very aware of how this could play out. So I think that behavioural side of it, and a lot of this is about behavioural stuff, and behavioural science is so important for that reason, I think was very important. And the one that you can tell I'm slightly obsessed with is this idea of that you waste money if you invest in something that you then don't need. We're going to see exactly that on the climate thing. There will be technologies which we're going to need to invest in, and we're going to need to scale, some of which will turn out to be wrong. And that's the price you pay for going with innovation. And the National Audit Office really needs to understand that, because as a civil servant, if you do something which then turns out to be seen as a massive waste of public money, and you're hauled in front of the Parliamentary Public Accounts Committee or the National Audit Office, you won't do it again. And that's what drives a very, very potentially conservative behaviour which will stop innovation.
Okay, go ahead.
You've spoken about the paucity of scientists in government and in Whitehall, and I sort of infer from that you're talking about people who are science literate. And I wonder, does the same go the other way? Is there a paucity of scientists who are, if you like, people literate? Because you've spoken about the difficulty in communicating complex things to politicians, let alone to the public, and politicians are driven by what the public wants them to worry about.
The short answer is yes, and actually it's quite interesting. If you look at most tech startups, they're very deliberately a mix of people with science, arts, humanities backgrounds, and that recognition that that integrated skill set is what's needed is, I think, absolutely right. And that's why I said, you know, it's appalling it's 10% STEM graduates, but it would be equally appalling if it was 90%. And I think that recognition of those different skill sets and abilities is a really, really important part of this. And I think, you know, scientists will often, and I've already alluded to this, come and say, here is the evidence, there you go. That's not going to do it, especially for somebody who's basically confused by the graph. They're going to say, well, thank you very much. Off you go.
Thanks very much for the talk. You mentioned in your talk the strengths in the UK in the design and conduct of randomized trials and actually the infrastructure that facilitates it, and also the question that you were asked when you went to Singapore. In the next pandemic, do you think that there is a much greater role for the use of randomization to assess the ways in which we implement things and actually evaluate them better? For example, the timing of the second dose of a vaccine or the use or value of boosters?
Yeah, I do. And right at the beginning, I had a lesson ringing in my ears, which was, I think it was during the swine flu outbreak when intravenous anti-flu drugs were being used, and there was a trial that had been set up to look at the efficacy of those drugs. And I don't know the exact numbers, so these are not the exact numbers, but something like 189 people in the UK, or 200 and something, had been given the intravenous flu drugs on compassionate use grounds, and one had been entered into a clinical trial. And it's completely crazy. I mean, so yes, randomization is important. Randomization, you know, it was brilliant what Recovery did, but the truth is it was still only something like 10 or 11% of people in hospital were in the study. Given that we didn't know what to do, it probably should have been 100% or close to it. So I think we've got to get this as a way of doing things. And yes, it could be applied to other parts of the interventions as well, although the outcome measures and ways of doing it are complicated for things like lockdown interventions and so on. I mean, it's much more difficult to think of the appropriate design, but I absolutely believe that randomization is a key part of getting to the answers.
So we have our last question.
So on climate change, I think you touched on something quite important, and you mentioned one Prime Minister that abolished this council. And I worry that there is a fault line increasingly in democratic countries where we might be in the wrong side of it, thinking it's an insider game to persuade a small number of people to legislate to get goals achieved. And the danger in democratic politics is you can see a swing against that. And I do worry about this, that we're losing the argument of persuading people that climate change, they might accept it's necessary, but I don't know that we have the technologies to persuade them to do it in a painless way. And I think we have mistakenly thought we can legislate a way to it as an insider game. And I really worry that we don't have time for that to, you know, the backlash is coming across the democratic world. And I do worry we might have misjudged this.
Yeah, I think we're in a very, very difficult situation with this. And I think there is a backlash in certain places around this, which I think is really, really damaging. Now, the truth is, it is difficult to make these changes. And certainly, if you go to the sort of far end of the behavioural changes, it's very difficult, and I don't think that's going to happen. So you've got to accept that there is a bit of behavioural change that needs to occur, and change that may seem rather small as an individual, when you multiply it by millions of people, is actually quite significant. So that needs to happen. And the technologies need to be backed, but they're not cost-free, and they are an investment. And I worry that the cost is confused for the investment. So if you believe that the rest of the world is going to have to do this, which it will, investing in technologies is probably a very good investment for what's going to be a multi-trillion-dollar market. And I don't think any of this has been really as honestly or clearly laid out as it should be as to what the upfront costs are versus the potential returns and what the difficulties are in getting there. But it absolutely needs to be done. I mean, if we don't get on with this, we're going to miss an opportunity. And I also slightly worry that the 2050 sounds such a long way off, whereas the truth is that if you don't do some of these things within the next 2, 3, 4 years, you can't possibly scale them in time for 2050.
Patrick, this period in your life has been one where you've been quite exposed, very much in the public eye. How have you coped with the stress of that? And so what advice would you give to people in that position? And I'm thinking of Angela, if she finds herself quite as exposed. Yeah, exactly. So, Patrick.
Yeah, that's point number one.
No diaries.
Although actually, one of the reasons I wrote some things down was exactly for the resilience point. You know, it was very difficult to not have some way of releasing tension. I mean, the key things for me were, first of all, the fact that Chris Whitty and I were working day in, day out together, and I had a partner who I could speak to was really important. I mean, if it had been a situation where the CMO and the GCSA had not gone on, it would have been very, very, very difficult, I think. So that was important. And the other thing that was personally for me was something that happened at home, which is our eldest son told my wife that we were not going to, because he moved back in during the first lockdown, we were not ever going to discuss it at home. And actually that was really important. And we didn't discuss it. We talked about other things inside, and that was crucial. And then a really, really important thing for me was my job was to give science advice, and as long as I was convinced that I'd given the science advice as clearly and correctly as I should have done, I couldn't agonize about somebody else's decision or approach. That was not my job to get anxious about. My job was to just make sure that people really understood what it was that I thought they needed to understand. And so keeping within your tram lines becomes quite important in this, I think. And I'm going to give an example when I went outside.
Patrick, thanks so much for speaking to us this evening. It's been wonderful.